All right, for all those people paying attention, hopefully everyone's having a great day. All right, class.
Yeah.
Thank you. All right, so we're going to continue on the 1.3 that we started on Friday. Yes, Friday. Okay. So continuity, add a number. So this goes along with some of the things that we had on the graph. One-sided continuity, add a number. So let the function be defined in the interval from open A to C closed. F is continuous from the left at number C. So it is continuous, it's considered continuous at C because it includes C. Let function be defined over the interval of closed C to B open, then is continuous from the right at number C. So the limit right here, so C from the right, it is continuous from there because it is equal to C, and that's what we're going for here. So continuity is not the same as limit, because if this, over this interval right here, limit at C would not exist because the left and the right both have to go to that number. But if there's no left and it's only asking for right, that means the limit from the right side exists, but not the left side, but it is still continuous.
Can you draw that, please? Because I got confused when you were explaining the difference.
There we go. This right here.
Okay.
So this is C. So right here, it doesn't exist on the left-hand side. Yes?
Yeah.
It exists at the point C, right? Because that's a closed dot. Yes? And the limit, that means from the right-hand side, it's going to this point right here, C, right? So it is continuous over the interval of closed C and, open B. There we go, like that. That's what that one looks like. This one up here would look the other way. So it is open A, and it goes to closed C, like that. Does that make sense? So at point C, it is equal and continuous. Does that make sense?
So C is continuous.
Because C has a closed. This C has a closed. So the continuity exists, limit does not. A one-sided limit will exist. This would be only a left-sided limit. But for a limit to truly exist, the left and the right both have to go to the same point.
So it
But
is continuous.
this one, it is continuous. It's asking about the interval. It's asking for, is there any holes in my roller coaster?
Oh, yeah.
There we go. That's what we're looking for. And it's asking for continuous at that point. So at that point, is there a hole in the roller coaster? No. Then we're good. All right. A function is continuous on an open interval. This is important right here. Open interval means I have a parentheses on left and right. So parentheses means, is that going to be equal to or not equal to? What do parentheses mean? Not equal to. Bracket is equal to. So this one is equal. This is not equal to. So that means my endpoints are not equal to A, and they're not equal to B. So it does not exist at A, it does not exist at B, but it approaches A. It gets really close to A, and it approaches B, really close to B, right there. So the next one right here, it's continuous on an interval. You notice it doesn't say open anymore. Interval, okay. Closed A, open B, okay. Right here, it is continuous on the open interval from A to B and continuous from the right at number A. So it's including open and also including from the right at A because A is closed. Same thing over here, okay, interval here. So it is continuous on the open interval But because B is closed, it is continuous from the left at B. Function f is continuous on a closed interval. Now, closed, okay, means both sides are equal, no matter what. Okay, there's no holes, no jump in the tracks, no bad roller coasters. So, continuous closed interval A to B. If f is continuous on the open interval A to B, continuous on the right A, continuous on the left B. So, that means that every single point in between A and B, there is no holes, no undefined, no bad thingies. Does that make sense? Is that nonsense? Or is it too early in the morning? You haven't finished your milk yet. Not yet. Okay. Here's example with pictures. And I really wish I could actually make the picture a little bit better, but no, apologize. Here is continuous A to B, so that means it's a closed dot here, open dot here. Okay, this is open, 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 open. This one right here, it is continuous at B, so that means it's a closed dot there, open dot there. This one right here, it is continuous A to B, so open dot there, open dot there. Okay, and this one right here, it is closed and closed. Is yours just really small? Okay, can you guys see it? Or
Someone see it.
okay, I'll rewrite it here so you guys can see. Closed A comma B parentheses. This one is A comma B. This one is A comma B closed. This one is A comma B. This one is bracket closed A closed B. Now the continuity is a big deal, especially when we're talking about the limits portion. That's the main reason why I wanted to reteach all of this over again. Determining whether a function is continuous on the closed interval. Now, if we were taking notes the other day, we would know that anything inside the square root has to be what?
Positive
Positive?
or negative.
No.
What are you talking about?
Okay, I gave you guys definitions of what this is going to be. What does this have to be to work? I wrote it on the board. I did. What can you not have in a square root? Can't have negative numbers, right? But can you have 0?
Yeah.
Okay, so that means that inside your radical, whatever it is here has to be greater than or equal to 0. That's important, and you guys need to understand this. Every time you see a radical, there is a discontinuity. There is going to be a problem, especially if there's a minus sign in there also. So this is your rule for this one. So all radicals have to be greater than or equal to 0. So let's take this and that has to be greater than or equal to 0. And we're going to solve for my values, and which is going to make this to be real or non-real. Yeah. So first thing I'm going to do, let's get rid of the square. How do I get rid of the square? I'm sorry, square root. Sorry. Get rid of the square root by squaring it, right?
Yeah.
Square both sides. 0 squared is
0.
So we get 4 minus x squared is going to be greater than or equal to 0. Now what do I do?
Subtract 4.
Okay, subtract 4. So negative x squared is going to be greater than or equal to negative 4.
And 2 multiply.
Yep, negative 1. So x squared has to be less than or equal to positive 4.
Right.
multiply or divide by a negative, you have to flip the sign.
Okay.
And then how do I undo the square?
Square root.
Square root. So x is less than equal to plus or minus 2.
Oh, okay.
Plus or minus 2. All right, let's see where that works out. So for these, we're testing it now. We're testing it. So now x has to be less than 2. Okay. X has to be less than equal to 2. So what happens when x is going to be less than or equal to 2? Let's plug it in. What are we going to get when we get that? I get 0, right? So if I was to look at a number line here, because that's going to be important for my interval from positive 2 to negative 2, and I'm checking for inclusion here. So can it equal 0? Can it equal 0?
Yes.
Yes, it can. So this is going to be 0, so that means that I would get a closed dot right here at 0. It says s has to be less than or equal to 2, so that means that it should be everything inside here, shouldn't it?
Yeah.
Okay, that looks like it's true. And it looks like it goes to 2 here. Now, let's go ahead and take a look at the next part. So this is the next part. Let's plug in negative 2 and see what we get. Negative 2 squared is 4, right? So that's going to give me 0. Okay, so that's going to be, again, 0 here. So do I have anything in here that it cannot be within this area from negative 2 to 2? No.
No.
I don't have anywhere, but if I were to have something outside of that interval, can I plug in 3? If I plug in 3, we get 3 squared is
Negative
9, right? So 4 minus 9,
5.
can I have the square root of negative 5?
No.
No. So that means that this does not exist out here. It doesn't exist over here at 3. So none of this. This doesn't work. So it only exists in between here and here. With that square root, that's important to understand because I cannot have anything that is going to be outside of that. Would I do the same thing if it was negative 3? Hopefully. Negative 3, if I do negative 3, I'm going to get the same thing because the negative, when I square, it's going to become positive. And so that means, again, none of this exists. So that means that it is continuous over this interval. If I were to take this to 3 or negative 3, I would say it is not continuous. It is not because it doesn't exist outside of 2 and negative 2. But it does exist at 2 and at negative 2. So that one is okay. It is continuous on the closed interval. Okay? Hopefully. Definition: continuity on a domain. A function is continuous on its domain if it is continuous at every number c in the domain. Determine whether the function is continuous on this domain. Okay, theorem. A polynomial function is continuous on its domain, all real numbers. A rational function is continuous on its domain. A function is continuous on an interval. Its graph has no holes, or gaps that are on that interval. A function is continuous on its domain. It will be continuous at every number in its domain. its graph may have holes or gaps at numbers that are not in the domain. So this last thing right here, it has holes and gaps outside of the domain, but we're only looking for to find for this one what the domain is going to be. So x squared times quantity of x minus 1. Actually, let me go back to this. Insert page. Like this. Did I write it correctly? Okay. So I know that everything in there has to be greater than 0. Okay. So let's go ahead and try it again. So right here, square it, x squared Now, this is a zero product rule. Anything times 0 gives me, say 0.
0.
Anything times 0 is, so that is a zero product rule. So anything times 0 is 0. So to make this statement true right here, I'm only going to be dealing with the equal part. To make this statement true. So let's see, x squared equals 0 and x minus 1 equals 0. I'm only going to work on the equal part. So let's look. So this one should be easy. Take the square root of both sides. X equals
0.
0. Good. Now this one right here, add 1, x equals positive 1. So x has to equal positive 1. Can it be more than positive 1? Yes, it can. It can be more than positive 1. So for this one right here, I'm going to look at my number line. So is there anything here that I plug in and I'm going to have a number that is going to be less than 0? So I know at 0, it's going to give me 0. So 0 is okay. So 0 is going to be okay. That's going to give me a closed dot right there. And at 1, okay, at 1, it's going to give me also a closed dot, isn't it? It's going to also give me a closed dot. Now, we're going to go through and try and figure out these gaps. Now that I have some places to start with on my number line, let's go and test places on my number line. What would happen if I plug in a negative 1? If I plug in negative 1, what's going to happen here? Negative 1 minus 1 is negative 2, right?
-2 times.
That's negative 2. But if I do a negative 2 squared, I'm sorry, negative 1 squared, that's going to give me,
1.
that's positive 1, isn't it?
Positive 1.
Positive 1 times the negative 2 is
Square root of -2.
square root of negative 2. Can I have that?
No.
No. So that means I cannot have anything over here. Let's check something in between. All right, I got two good dots right here. All right, so let's see. 1/2 squared is
1/4.
1/4. That's positive, right?
Positive.
So it's a positive number. That's important. Okay, and then 1/2 minus 1, negative 1/2. So can I have a negative 1/2 inside my radical?
No.
No. So that means that nothing inside here works. It works at 0 because when this is 0, anything times 0 is,
0.
even though that this would be a 0 minus 1 is negative 1, right? It's still going to give me 0 because my x squared is going to give me 0. So that means that there was it exists right there, nowhere else over here, and at 1. Okay, let's try numbers greater than 1. So when I plug in the x squared, any number is going to become a positive, isn't it?
Yes.
Good. Any number is going to be a positive, and so the only thing that matters is what's the sign of this second one. So that's 2 minus 1 is?
1, positive 1.
Positive 1. So a positive times a positive is?
Positive.
Positive. So do I have to worry about having any negatives because of that?
No.
No. So we're just looking for sign changes now. So we simplified it even more to see if there's a sign change. So we know it exists here. Do you think it's going to exist over here too?
1.5,
Yeah, it is. It's going to exist for everything. So from here, now on my interval is going to go this way. All numbers greater than 1, equal to 1. So it's from 1 to infinity. But there's also that weird little thing way over there at 0. It, two different notations you would have from 0, bracket, union, 1 to infinity, parentheses.
Oh.
So because that little weirdness right there with that x squared, that's where we're going to end up with. Make sense? Nonsense?
Yes.
Hope so. All right. Properties of continuity. So these composite functions, I'm pretty sure we're going to have to do a whole bunch of these that are one-to-one and looking at these because this is going to be a big part of the AP exam. So I could probably read this to you all day long and you're not going to understand any of it. So, because composite functions is going to be important and it works better if I actually have a table or a chart to go along with it. So when we actually do this one in real practice, I'm going to give you a chart for that one. So to understand that. Now, this is important right here because this actually has its own set definition. This is actually so prominent in calculus, it's just IVT. It's referred to as IVT, intermediate value theorem. So here's the basic definition. I'm starting right here. Isn't there Lux across the street over there?
What's Lux?
Yes? Okay. Yeah, Lux is across the street. I don't know. It's some place that people get coffee and like bagels and stuff. Anyway, so I somehow end up at Lux that is on the other side of Central.
Mm-hmm.
Intermediate value theorem says no matter how I went there, I somehow had to cross Central.
Cross a certain point.
Yeah, I had to cross a certain point. Even if I went there, I came back, I got all the way over there, I had to come back, I left my wallet in my truck, had to go back again, but my end point, so I start here, I end there, therefore at some point in time, at least once, I crossed Central. That's what this means right here. That's what all this is. So, let f be a function that is continuous on a closed interval. That means that it is closed, there's no gaps and jumps. Okay? N is any number between f of a and f of b. So this would be my a, and this would be my b right here. Then there's at least one point c on the open interval for which that it is equal to this value here. So there's some point there that I had to cross. To get a better idea of results, suppose you climb a mountain starting at an elevation of 2,000 and ending at an elevation of 5,000. No matter how many steps up and down you take as you climb it, some time in your altitude must have been here, which is my 3,765.6 meter altitude, or any number between those. So somehow I had to cross there. the chicken does cross the road. We don't know where, we don't know when, but somehow the chicken crossed the road. Use an intermediate value theorem to show that has a 0 between 1 and 2. Okay. So between 1 and 2, that's my interval. And so if you were paying attention, what type of interval is this? Intermediate value works with what type of intervals? Closed intervals. Closed intervals. So what could I do with those values there?
Brackets.
I could. So I can go from 1 to 2. If I know that they're closed, what could I do with those values? Can I plug them in?
Yes.
Yeah, let's plug them in. So plug this in. It's going to be f of 1 is equal to 1 cubed plus 1 squared minus 1 minus 2. 1 plus 1 minus 1 minus 2, which gives me, what's that going to give me? Negative 1. Yes? Okay. Let's try the other side. Two cubed, 8, plus
4.
4 minus 2 minus 2. So what are we going to get here?
8.
8. So now I will show you by graphing this. So this does work, and I'm going to show you by graphing it.
Does your calculator work?
Nope. Okay. On a closed interval, f of 1 gave me what value? Negative 1. So there is a closed dot right there. F of 2 gave me
8.
closed dot right there. And 0, isn't 0 right there on the x-axis?
Negative 2.
Isn't the 0 right there? Okay, so now using intermediate value theorem, at some way, some point, to go from here to here, I had to cross the 0, right?
Yeah.
This is where intermediate value theorem is actually used the most. Seeing that if it crosses the x-axis. It's asking if it has a 0, so just by looking and seeing, this one right here was a negative, and this one is a positive. So therefore, if there is a change in between the signs, there must be a 0 in between there. So even if it went from negative to positive, it had to cross 0 at some point, right?
Yeah.
That's what that means.
Okay.
Now, we're not going to do the calculator portion of this because I get the better graph. My graph is amazing. But yours is going to look better, right? Because you guys are just that much better than I am. All right, so there we go. And we are done with that. So make sure you all like, share, and subscribe. Hit that notification button. Support my channel. Buy stuff from my merch store.